Today we're going to talk about WholeLife with Welds. Start with just kind of introductions. We're part of Francia, which is a division of HBM, and we're basically responsible for software. And so we'll have two brands of software, nCode and ReliaSoft. We also provide training, instruction, services, material testing. Looking at the two portfolios of software, ReliaSoft contains tools for doing reliability, things like Weibull and BlockSim, XFMEA. On the nCode side, we have software going towards durability, DesignLife, GlyphWorks, VibeSys. Today we're going to be focusing on DesignLife, looking at the introduction of WholeLife welds into DesignLife. Today I'm going to go in and just start initially, just kind of giving a brief overview of fatigue life of welds, and then transition into a discussion on how the WholeLife methodology works, and then talk about how that's been integrated inside DesignLife to look at weld fatigue. We'll look at some correlation work that was done with a project done by SAE, and then finish up with a summary and questions. Basically, when we look at fatigue predictions, we have a pretty straight process that we use. However, when we start looking at welds, that process tends to break down. One thing we see is the fatigue properties of a welded joint are very, very different than that of the parent metal. The weld joint has huge stress concentrations due to the geometry left in the welding process. There can even be things like cracks initiating at toes and roots already. It can leave extremely high residual stresses to the welding process unless those have been relieved or removed in some way. There's also a non-uniform distribution of material properties due to deposited metal, heat-affected zone. One of the things you'll see, and we can see on the right-hand side, where we have kind of just a description of stress life curves for different components, that the fatigue behavior of the welded component is significantly weaker than that of the parent metal, or even the parent metal with notches. Another thing we tend to see is that the parent metal strength doesn't tend to show up in the fatigue weld strength. Finally, just as a focus, because of existing crack sites and the types of damage we see in welds, fatigue behavior of welds tends to be crack growth. We look at ways to actually analyze welds. There are several out there. One, as we said, is crack growth. Historically, we haven't done a lot with crack growth because it tends to be expensive to calculate. It tends to have a lot of inputs in terms of trying to decide where the crack's going to be, what direction it's in, what's its shape. So it tends to be a very point-wise solution historically. There's another approach, local notch stress, where we're going in and modeling the welds in pretty fair detail, trying to go in and describe as close as possible the stress at the critical locations. Now, this is very difficult to do, again, because of the geometry of the weld toe, but this is another approach. The third approach, and the one that historically we have used, is using structural stresses as a damage parameter. Here, instead of trying to capture the detailed stress at the critical locations of the weld, what we do is measure some sort of, if you wish, nominal stress that we can use as the damage parameter. And this may be nothing more than a strain gauge at the toe of the weld. It may be using hotspot approaches like we see in the offshore. They can be using structural stress calculations either from nodal forces and moments or through thickness integration. And historically, that has been the approach that we have used for a great deal of our weld calculations. An example of that is seam weld against spot weld follows a very similar approach. The way that these damage curves are actually implemented is starting out with a whole series of actual physical tests. And so I have all these different specimens. We go off and generate load life curves. Now, because the specimens have different gauge thicknesses and different part geometries, there's a huge scatter in these load life curves. The key here is to go in, take those individual specimens, model them with a fine element modeling procedure that we have defined as the way we're going to represent a weld in a part, and then back calculate out of those specimens the structural stresses that come from this. And again, the structural stresses tend not to be the stresses on the part. They may be stresses that we calculate either from nodal forces or through thickness integration in solids. Those structural stresses are then corrected with a variety of corrections, things like part thickness, loading ratios. And what happens is that they tend to go in and collapse all these damage curves that were individual load life curves down to a single curve that we can use for fatigue prediction. And this works relatively well. Again, one of the things that we have seen is that the weld strength really isn't a function, as strong a function of the parent metal. And this has worked very well for decades. However, there are times when this approach isn't all that useful. And one of the things that the structural stress approach doesn't do is really capture details about the welds. Without that, we have no way to really go in and model things as improvements in the weld geometry or in the welding procedure to try to get more strength out of the welds or prove there's more strength. You can see we have here a weld curve that was collapsed from a series of tests, but the first thing that you start to notice is that it looks like it's fairly well collapsed on the line. But if I go off and look at 100,000 to a million, you'll see that I have data points there that actually the width of that scatter is more than a decade. If we want to use these curves, we have to basically be on the conservative side, which doesn't allow us a lot of flexibility into try to redesigning. So to go off and look at ways that we can go in and predict more precisely weld fatigue, we're going to go in and take a look at crack growth. The reason for this is that there are times when we're looking at welds where we have a great deal of control on how the weld is done. We're actually going to go in and design the weld rather than design the geometry to be welded. And so here in the upper left-hand corner, we have a weld where I have the flexibility of maybe grinding the parts to different bevels to control the weld penetration. I have choices in how many passes and what order of the passes do I take to weld that part together. I may even have the ability to go in after the fact and grind away continuities or shopping it, stress relieve it. Things like that can drastically improve the weld performance, but I don't have the ability to do that with a structural stress approach where the structural stress is a damage parameter. We can see how that's very, very powerful in areas where people have things like construction equipment where we have very, very large welds. However, this is becoming even obvious for use in things like automotive, where now due to lightweighting, we're starting to see new structural geometries, things such as extrusions and castings that are being welded together to basically form a specific important joint. And again, these welds can be designed rather than taking the parts and just welding them like we have with sheet metal and body structure calculations. What we're bringing out here today and talking about is basically a new capability inside of DesignLife for welds. It's based on a theory of crack propagation that was developed by Dr. Glinka out of Waterloo. And it's using this style of crack growth capability to go in and now to analyze welds in more detail. What we've done is taken this and actually implemented it inside of DesignLife, being front-ended by our standard seam weld technology. It is able to go in, identify critical welds from the first pass, and now go off and do more detailed analysis at critical locations. It's set up to support multi-axial loading. It's set up to go in and bring in data about the welds to give us more information, things like residual stress profiles that have been either simulated or measured on the parts. So that's what we're going to talk about today. And starting with, let's just kind of go back and take a look at the WholeLife methodology. So what we're looking at here and how we're proposing crack growth is thinking of crack growth as being a whole series of initiations. Typically, when we look at crack growth, that we assume the crack tip, it comes to a sharp point, leaving us with basically an infinite stress at the crack tip. The concept that Dr. Glinka has proposed is that crack growth is actually failure grain by grain as the crack proceeds. And when we look at the tip of the crack, it's not a sharp point, it's actually a blunt notch. And that blunt notch has a geometry similar to the grain that has failed. Taking this idea, it gives us the ability to go in and to predict the stresses in detail in front of and actually back of the crack tip, where historically we've assumed that they were singular and used just empirical rules to do things like crack closure. Now we have the ability to go in and actually track the stresses in front and behind the crack tip and do a more thorough calculation. The other thing this actually buys us is the starting point for this crack growth is actually a material property. Here it's called Rhostar, but what Rhostar is almost the same size as the grain structure. So we now have a starting crack size that is well defined. That's not one of the issues that we have to overcome in using crack growth and trying to guess at what the initial crack size is. So the actual crack growth model is pretty standard. What we have is something that looks like Paris law here, the DADN. The only difference here is that we're using delta kappa rather than delta K, stress intensity. And this delta kappa is actually a function made up of stress intensities. If you look at the equation for delta kappa, you'll see that we have stress intensities, and they're put together with what looks like a Smith-Watson-Topper calculation. So what I have is a parameter, stress intensity max, that's looking at the peak value, and now I have it multiplied by a stress intensity range, max minus min. Walker is basically Smith-Watson-Topper is just a subset of Walker where the p-values are both 1/2. The stress intensities themselves are calculated, okay, can be calculated a variety of ways, but they include the far field stress that's being applied to the crack. They include things such as the crack length, crack geometry, which is that Y parameter. Here's one of the things that we're bringing into the stress intensity is also the stress intensity from the residual stresses due to the crack growth process. That's that KR. There's also a correction to deal with very, very small cracks sitting around the same dimension as the grain structure. The way that we're actually calculating the stress intensities are through things, through weight functions, actually also provided by Professor Glinka. And the concept of a weight function is that if I provide the weight function, a stress profile through the crack path of the uncracked section. So the stresses I'm predicting are the stresses without the crack. Taking that along with the weight function, I can calculate a stress intensity for any length crack. The benefit of using weight functions is they support a wide range of loading types, and actually are applicable to a wide range of geometries as well, because all we really need to do is describe to the weight function what the stress profile is. The one we're using inside of WholeLife for the crack growth is a semi-elliptical crack sitting in a plate, and it has the ability actually to change its aspect ratio. So it may start out as a thumbnail crack, a half circle, and depending on the stress state as it's growing through, it can change its aspect ratio and change into any form of ellipse. The other thing we're going to leverage here is the fact that these stress intensities are coming from elastic results prior to us going in and doing plasticity. So we're able to actually take these and superimpose them, which will be important downstream. Visualizing the crack growth process sitting inside of WholeLife, we start with a existing crack, maybe sitting at Rhostar, and it has a blunt tip at the notch, which means that we can go in and accurately represent what the stress state is in front of that crack tip. Now, one of the things that we do see is that these are all elastic calculations, so we end up over predicting the yield stress typically with this, and what we do is basically back down the stresses to the yield stress and then redistribute the energy in front of that crack. So we're just basically going off and predicting what the effect of the plasticity will be in front of the crack. As we march through cycle by cycle, basically loading peak and valley, we're going through this calculation of redistributing the plasticity, and as we march through the crack, we're developing a profile of the residual stresses in front of the crack as well as behind the crack. And the stresses in front of the crack are what we use to basically drive the retardation in the crack growth. The stresses on the behind the crack tip are used to predict the crack closure. So using that crack growth approach, and one of the hallmarks of this approach is the fact that it actually is starting at the initial grain size of the structure, so it's actually starting at initiation. So we're basically bringing in both initiation and crack growth into the same calculation. We've taken that and we've implemented inside DesignLife for Welds. And the way this is going to work is we have a structure that's been created to do weld fatigue using the standard seam weld technology, and that could be a coarse solid model or it could be a shell model. Again, we're not really forced to use a very detailed model to get the loading that's going into the welds. We use the standard seam weld approach, going in and specifying multiple locations, either as you see here in the upper right hand slide, where I have all these different locations at weld toes, weld roots, through the thickness, through the throats of the welds, specified for a seam weld calculation. After the seam weld calculation's done, we go in and identify those locations that had the most damage and then rerun them using WholeLife with crack growth. Again, that gives us the ability to identify the locations that we need to analyze. This is able of going in and looking at complex geometries, complex loading, so I can have multi-axial loadings applied to this structure. And again, with the addition of additional parameters in terms of material properties for crack growth and descriptions of the stress profiles, we can go in and use the full DesignLife model to drive these crack growth calculations for welds. The inputs to DesignLife WholeLife Weld is an FE model, and again, an FE model that is not necessarily that detailed around the welds. It could be a shell model using basically grid point forces and moments to calculating stresses. It could be a coarse solid model where we have through thickness integration, again, calculating stresses. But we apply full sets of loads to our structure, and then we do specify locations to analyze. And again, that's going to be either identifying the shell elements in our welds, or going off and specifying locations via weld configuration file for solid welds. Each one of those locations are associated with things such as a stress profile across the weld path. It could have, in addition, residual stress information along that weld profile as well. And that could come from either measured or simulated calculations trying to predict the residual stresses from the welding process. And then we also point to that additional material properties required for the whole life calculation. And again, those are crack growth curves as well as stress strain behavior, because internally we're going to be doing plasticity calculations for the crack growth. Allowing us to go in and deal with multi-axial loading, the way that we have approached this is that we take all the loads coming into the structure, and for each load we go in and we apply a unit load in the direction of that loading at that particular load point, and we calculate a structural stress from that. Again, these structural stresses can be either from the shells or from the coarse solid models, but what they represent is a definition of a linearized stress for a typical, a particular loading mode. And the two loading modes that we're focusing on are membrane and bending, because those are the dominant loading modes for these cracks that we're looking at. And so in this case, I have a unit load applied to my structure. I take and analyze the path where the weld is going to crack through, and I linearize the stress here, and I capture the membrane portion of that stress. Again, the membrane portion would just be the part that would be a uniform stress across it. I take that structural stress value and I multiply it by the force history. And what I get now is a structural stress history for that particular load. And I can go off and duplicate this for each load in my structure. So for each load coming into my structure, I'm going to calculate a structural stress history. You could think of these as basically nominal stresses that I'm going to go in and use as the driving far field stress on my crack. Once I have all of these histories calculated, I sum them up and I get a structural stress history for membrane behavior of that crack. I can then go and do the same thing again, but now calculating bending. So I'm looking at bending stress on the structure rather than the membrane stress. So I could have on my structure dozens of loads coming in, hundreds of loads coming in, and I'm going to basically condense them down to two load histories. And those load histories have been converted into a structural stress for membrane behavior and a structural stress for bending behavior. And I'll have one of these sets for each location in my structure. So these right here are actually unique to each location being analyzed. Those stress histories are, again, you could imagine them as a nominal stress. what I'm going to need to calculate the detailed stress through the part is a stress concentration factor. So the second piece of the input is stress profiles. These are actually KT profiles because what they are the multipliers on my structural stress to calculate the actual stress. And these KT profiles, I need two of them. I need one for a membrane load to go along with the membrane structural stress, and I need a second for the bending load. These can come in a couple different paths. One, we've built into the WholeLife Weld a parametric fillet model. This is actually from Monahan, where I can go in and specify parameters in terms of part thicknesses, weld toe radii, the angle of the weld bead, and it will generate an empirical profile of KT through the weld path, one for membrane, one for bending. So that's one way to actually do this. There's a second where I can go in and literally import these profiles as files that have been computed by another process. And we have built into WholeLife Weld another glyph that allows us to go in and specify a path through the part. And here the path through the part would be described again as a solid weld, where I specified the location and direction to describe that path. And this glyph goes in and evaluates that path through the part, looks at the stress from a load case through that part, and can then go in and basically predict what the stress profile along that path is. And that's actually could be used directly as it is if I have a part where I can very easily go in and load it to generate a stress state at this location, this pure membrane, a second stress state, this pure bending. That's not always the case with our parts. So there is actually a second portion of this glyph that allows us to go in and to give it just two arbitrary load cases. So I bring in a detailed model of the path through the structure. And here's one place where up to now we've looked at modeling that was relatively coarse, looking at the entire structure. We now are going to go in and take the paths that we want to analyze and model them in detail. It could be done in the actual structural model. In this case here, I have a breakout model where I replaced a path that I'm going to analyze with a much finer model. And now I'm predicting the stresses through that fine model. Again, these are going to be stress concentration profiles across that part, so we need to have a relatively fine mesh. We then apply two arbitrary loads to that structure, and the stress profile glyph can go in and back out from these two arbitrary load cases what the detailed KT profile is, one for pure membrane, one for pure bending, write these out where we can actually import them into our DesignLife weld calculation. With this, I can take any complex geometry, apply two load cases to it, and describe which paths I expect to see failure in my from weld failure, and develop not only the loading going in, the structural stress histories, but also the detailed KT profiles allow me to go in and develop over time detailed stress profiles on the crack path as we have changes in loading. So I have loads coming in. I've specified locations that I'm doing these calculations. Again, either shells that are going to specify as welds or the solid weld locations. I bring in the stress profiles in terms of KT profiles for bending and membrane. And now the last piece I have to bring in are material properties allow us to do crack growth. And this is actually two sets of curves. One, a standard stress strain curve we'd use in DesignLife. Part of the calculation method is going in, predicting the elastic stress in front of the crack tip, and then applying plasticity to it to redistribute the energy. And so we need the Ramberg-Osgood curve here to give us the stress strain behavior. The second piece is a crack growth curve in terms of this delta kappa that we are going to use to describe the crack growth, and we'll talk about that in just a second. Lastly, there's some additional parameters, things like the yield stress. We'll need a yield stress to allow us to go in and do some of the plasticity calculations. We need to know fracture toughness values because failure can come in a variety of ways with crack growth. Besides having cracks go all the way through the part or hit some sort of user-defined length limit, we could also be looking for fast fracture. So we need to know the K1C of the material. We do need the Walker exponent. That Walker exponent was the exponent that was used on the Kmax, the Kmax and the K range. We actually have an approximation for that using just N prime from Ramberg-Osgood, so that's taken care of. The last parameter that we need is Rhostar. Rhostar is the initial crack size as well as the assumed increment that we kind of initiate through. Again, this relative to grain size. The way it's actually calculated is in a routine that we use to create our damage curves, this delta kappa crack growth curve. The inputs to that are a series of standard crack growth curves using just standard stress intensity ranges. And we have these for a range of R ratios. We then have an algorithm that will take these and basically collapse down them into a single curve. So now we have a single curve that describes crack growth across multiple loading ratios. And the output of that is actually our estimate for Rhostar. So this Rhostar, this initial crack size, and again, the kind of the crack increment that we use to initiate through is part of this material fitting parameter. So we have implemented inside of DesignLife Weld a crack growth procedure that goes in and does initiation and crack growth with the assumption that we have this blunt notch in front of, basically as the tip of our crack. It is actually driven from standard seam weld solutions initially to first go off and identify locations, and then secondly, the structural stresses that were calculated for our standard seam weld are now really the loading going into the crack growth. And then we have mechanisms to bring in the remainder of the crack growth information that we need. We're now just real quickly, just look at how we started some of the validations for this. We have here a project that was done by the Fatigue Design Evaluation Committee of SAE over a process of about 5 years. And what they were looking to do was to try to validate this concept of total life. Total life being both initiation and crack propagation to describe welds. And to do this, they went through a very detailed project where they created welded specimens. They also created machine specimens that matched the weld geometry without the welds in them. They went through a wide range of material characterizations, both for strain life as well as crack growth of this A36 material. They have done detailed measurements of the weld toe and weld root geometries. They have gone in and done physical simulations as well as experimental tests to calculate residual stresses on these components. So they have really characterized this component to a great deal, and then have taken these welded and actually non-welded specimens and run them through a wide range of loading types, some of them being constant amplitude loads with different ranges of R ratios, looking at tension, compression. They've looked at block loading, going in and looking at how underloads would affect the crack growth, and then have run actual full-time histories of random loads through this as well. And with that, they have tested numerous specimens with a tremendous amount of detail in terms of measuring failure to growth, having images, camera, or basically movies of the crack growth over time. So we have not only detailed specimens, but we have fairly well-defined crack growth failures. And taking that geometry, the loadings that they used, the FE models that were used to calculate the initial stress profiles that we've used inside of DesignLife, we're able to go in and, using the material definitions they've already created in terms of crack growth and strain life, go in and do the whole life weld calculation. And again, on here, what we started with was our T specimen, and we actually had weld locations on both sides of the model. Some of these loadings actually go in, are either fully reversed or are loading in both directions. So which side of the model starts cracking first is in question. And so that initial calculation is done just with standard seam weld, looking at the stress histories on the model. The critical location is then turned around, and we do crack growth through that path at the critical location using the whole life methodology. What comes out of this is actually fairly detailed information in terms not only of number of cycles to failure and why it failed, but growth histories for these. And in this particular flow that we put together, we created a report, and coming out of this was things such as the structural stress history going into the component, things such as the growth curves. The red curve is actually the growth through the part. The blue curve is actually the growth of the crack as it widened out. The stress profile in this part basically has a stress riser at the weld toe, and so the crack grows quicker basically in its width than its depth. And then finally, we specified several different crack geometries through the life of the growth, which you see down here. Going in, taking all the test data, taking the predicted data, we've gone off and plotted these on a curve where on the horizontal axis I have the test life that was actually measured by SAE. The vertical axis is the predicted life for each of those tests done by WholeLife. So theoretically, if I was on the diagonal, I have an exact answer. The green line is a factor of 2 in life conservative, and then the red line is a factor of 2 in life unconservative. And what we've plotted are all the specimen tests that were done on the welded specimens here. And you'll see that we have a fairly tight scatter band for a crack growth for a weld calculation here. We have, basically sitting in a scatter band of 2. Now, coming back and looking at this, we have taken that same information and we've actually run it through our current seam weld capability. So again, looking at the standard seam weld approach, we end up with a curve that represents kind of the average behavior of a weld. In order to actually use that, we have to go in and to be conservative on our calculations and basically push our weld curve down such that we capture the majority of the test parts. So what we've done is reanalyze those weld specimens, and you see on the right hand side we have the WholeLife predictions still there, but we've laid down here the seam weld predictions. And you'll see that the seam weld predictions are substantially more conservative than the WholeLife. The key here is in order to go off and to get a more precise answer, we had to have more information. We had to understand a lot about the welds, which many times we don't have. And so the seam weld approach is not replaced by WholeLife, and probably 90-95% of our customers, they'll still be using that because of their limited knowledge of what the actual welds look like. However, if you want to go off and do a more precise calculation on a detailed weld, we have the ability to do that. And actually, I just wanted to reiterate the structural stress approach that we use for seam weld. We go through and we calculate a structural stress here where the structural stress is actually the damage parameter. So the way that we generate stress, be it grid point force calculations, be that through disintegration, we actually use that as the damage parameter on the vertical axis of our component life curve. And this SN curve is not material. It's not weld material. It's actually the behavior of a unimproved MIG or MAG weld in steel. Again, it's generic. It can be used against any weld with the overconservatism. What we're doing in WholeLife is we're taking those structural stresses. In fact, that's what's coming up here. We're bringing in those structural stresses, and the first thing we do with those structural stress histories that were the damage parameter in seam weld is we multiply them by the KT factors that are the stress concentration factors across the weld path. So now we actually have a detailed stress along the weld path over time. That is used in a calculation for stress intensities that now gives me a detailed stress intensity over time as a crack grows. And those stress intensities are put together into our delta kappa. Again, this right here is a combination of stress intensities that not only deal with the range, but also the R ratio, such that we now have our damage parameter. So we're using the same structural stress calculations, but those are now just the beginning of an input for crack growth. And coming back to this slide looking at the comparison between the two, the takeaway here is we can use the standard structural stress approaches if what we have is a limited knowledge about our welds. What are the welds going to look like, weld toe geometry, things like that, stresses left, in the weld due to welding process. The more we understand about the weld, its geometry, its residual stresses, the more precise we can be with WholeLife. So, ending this, what we have is WholeLife is actually a unified approach to fatigue. It incorporates both initiation and propagation due to the fact that it's using this blunt notch at the tip of the crack. We've implemented that approach as a weld fatigue calculation inside of DesignLife. And the way we have done this, it actually allows us to do crack growth very seamlessly inside a finite element-based solution. It handles both complex loading, so I have multi-axial loading coming in, as well as complex material geometry. It allows us to go off and use the knowledge we have about our weld to improve the prediction. So I'm not going to guarantee it's more accurate, but it's definitely more precise. And so this actually is really focused at places where we have critical welds, places where we have a large construction equipment where we're going to design the weld rather than design the part. Again, looking at things like lightweighting, where now we're starting to see different architectures where we're coming up with components cast, extruded, where the connection is now a fairly important weld. And we've already gone off and shown that we can go in and correlate to actual test data to do this.